Section 10.1, formulas for sum of cosines and sum of sines. So these are our sum formulas. We're going to be adding or subtracting two angles together and seeing what's going on here. So, for example, if I ask you to find without a calculator the sine of 15, you might think, well, the sine of 30 we know as a ratio is 1/2. So you would think, okay, that means the sine of 15 would probably be half of that. And we can find that out using the sum formulas here. So let's see what we get. The sine of 15 also could be found once we talk about how we use these laws here by thinking about sine of, for example, 45 degrees minus the sine of 30 degrees. And if we know the sine of 45, is a 1 over root 2, the sine of 30 is a 1/2, and we would just simply make common denominators here. We get root 2 over 2 minus 1 over 2, and we get root 2 minus 1 all over 2. It's the exact value of the sine of 15. Well, let's see how we do this using our sum and difference formulas for sines and cosines. First, we're going to derive where they come from. We have our unit circle, radius of 1, and we'll start out with this angle beta here. We introduce a new angle, angle alpha. And with that angle, we have this point on our circle we'll call point A, and it has the following x, y values, cosine of alpha and sine of alpha. And our point on the unit circle for angle beta we'll call point B, and that has x value of cosine beta, y value of sine beta. And if we took alpha, which right now is this whole angle, and we removed from it the beta angle, we would get the difference of alpha minus beta as our angle that creates this triangle inside of our unit circle. And we don't know if that's a right triangle, but that's okay because we have some laws of cosines and laws of sines that we could use to find this angle. So first what we're going to do is we're going to look at what is the sum or difference of these angles. We're going to look at alpha minus beta for this example for cosines, and we'll use the law of cosines to find this length AB, line segment AB squared. So we set up our law of cosines, and we would get that AB squared would equal the length of OB, which is going to be cosine squared B plus sine squared B. Just using the imagining a triangle created there with angle beta, and we have hypotenuse, just 1. So cosine squared plus sine squared is where we're getting that 1 from. And we square that. And then plus the other side, now we're talking about the alpha angle, cosine squared alpha plus sine squared alpha, also a 1 as a hypotenuse there, minus 2 times each of those lengths, so 1 times 1, and the cosine of this angle alpha minus beta. All right, we get, simplify this, 1 plus 1, 2, minus 2 cosine of angle alpha minus beta. So that's what 8b squared is using our laws of cosines. Let's go and develop this now for our other one. What about using the distance formula from those points A to B? So now we're looking at this line segment AB from here to here, using distance formula where we say distance squared is equal to difference in x value squared plus difference in y value squared. So our difference in x values, cosine beta minus cosine alpha squared. So now we're taking a look. AB squared is equal to cosine beta minus cosine alpha quantity squared. There's my difference in x's. And we're going to add to that my difference in y's. So we have now our sine of beta minus our sine of alpha squared. Go ahead and do some work on this. We get cosine squared beta minus 2 cosine beta cosine alpha plus cosine squared alpha. Cosine squared stuff, but they're not the same angle, but that's okay because we're going to end up with some common angles in this next setup here. Now we're going to do sine beta minus sine alpha. We're squaring that. Sine squared beta minus 2 sine beta sine alpha plus sine squared alpha. Again, seeing some squared things. So the cosine squared beta and the sine squared beta make 1. And then we also have the cosine squared alpha and the sine squared alpha making 1. So we simplify this. And we end up with 1 plus another 1 minus 2 cosine beta cosine alpha minus a 2 sine beta sine alpha. Simplifying it, 2 minus 2 cosine beta cosine alpha minus 2 sine beta sine alpha. And now we get AB squared using the distance formula. So we take those two values, or 2AB squared. We have that one from law of cosines. We have this one from our from our distance formula. And now we set them equal to each other. So we're going to have 2 minus 2 cosine alpha minus beta. There's the law of cosine setup. And then that's going to equal the distance formula, cosine beta cosine alpha, minus 2 sine beta sine alpha. And then let's see what we get here. We're going to solve for the cosine of alpha minus beta. So first we subtract the 2's. They get to go away. And then we're going to divide out this negative 2 over to this side. And we get cosine of alpha minus beta is equal to cosine beta cosine alpha plus sine beta sine alpha. And there is our difference formula for cosine. And let's see how we would develop the same thing with our sine. So if this was a cosine minus a negative angle of beta, so as in this example down here, see what happens is we introduce a negative angle, and we know from our even odd identities that a negative angle produces a positive cosine value, so that's why that just becomes cosine. And here a negative angle in sine would produce a negative value of that angle, sine beta. So we get this sum, so the negative part makes alpha plus beta, and we get our second cosine formula. So the difference and the sum of cosine angles alpha and beta. Okay, let's carry this on now and take a look at what happens with our sines. sum difference formulas for sines. Sine alpha plus or minus beta. Consider our cofunction relationships for sine of theta. Sine of theta we know from cofunction means cosine of 90 minus theta. What we're going to do is we're going to substitute that theta value with this theta equal alpha plus beta. All right, so doing that, we get sine, substituting theta with alpha plus beta, we get this. It is equal to the cosine of 90 minus this alpha plus beta. Doing a little work there inside the parentheses, we get 90 minus alpha minus beta. All right, now here's where we're going to be a little creative and recognize that what I've got going on here is if I were to pair this 90 minus alpha together, we'll call that some angle. Then I have a situation where I have a cosine of some angle minus another angle. And we just learned from our previous example that a cosine of an angle minus another angle is in the setup of cosine of that first angle times the cosine of the beta plus sine of that first angle, sine of the beta. So where did that come from? That just came from the derivation we have for cosines of an angle minus another angle. Cosine alpha, cosine beta plus sine alpha, sine beta. So that's all we've done. And then we look at the fact that cosine of a 90 minus an alpha angle and sine 90 minus an alpha angle, this is simply a sine value of alpha. And sine of 90 minus an alpha is the same thing as a cosine of angle alpha. That's just from our cofunction relationships. So then we finally get down to the sine of alpha cosine of beta plus cosine of alpha sine of beta. And that is what sine of two angles adding together would become. And that's our sum formula for sines. And then along the same concepts as we had for our what goes on when there's a difference. So now we're going to add a negative angle in here. And the negative beta, again, a negative cosine just develops into a positive cosine. Not the case, though, with the negative sine value. A negative rotation in the angle produces a negative sine value. And so that's why this becomes a negative here. So a sine minus an alpha becomes sine cosine minus cosine sine. So the thing to remember, with the sine sum and differences, if I am adding two angles together, and my formula will also be an addition symbol. And if I'm subtracting two formulas, I will be subtracting here. Now there is a little saying to help us remember the sum of sines and the sum of cosines. Let's go back to the cosines real quick. Sum of cosines, notice that cosines begin with cosine, cosine, and then they end with sine and sine. And so that's one way to, just a little, I guess, a mnemonic way of remembering this. Cosines are going to be cosine, cosine, sine, sine, and then they are opposites. So a sine or a cosine of the difference of two angles results in the sum of the cosine, cosine, sine, sine. And the cosine of a sum results in the difference of cosine, cosine, sine, sine. So cosine, cosine, sine, sine for sum or differences and think opposite. And for sine sums or differences, you do sine, cosine, cosine, sine. And you have the same sine values in terms of SIGN, plus to plus, negative to negative. All right? Just think of the cosines being the bad guys. So they're going to always be opposites. I don't know. Maybe that's helpful. Opposites there for the cosine because they're the bad guys. All right. So let's use these. What do we do with them? Well, we kind of saw what we did with them with the sine of 15. And we said sine of 15 is equal to sine of 45 minus sine of 30. So what we're going to be working with are the angles that we know of from our right triangles. 30, 60, 90, 45, 45. So little refresher, put our angles in here. There's our 45, 45, 90. Here's our 30, 60, 90. And the appropriate relationships between their sides. So what would we get, again, without a calculator or our trig tables, how do we find the sine of 285? Well, it's between 270 and 300. We know the sine of 270 is negative 1. We know the sine of 300 is a negative root 3 over 2. But how can we use some known relationships angle-wise for sine to help me come up with 285? Well, some ways to come up with 285. I can do, let's see, the sine of 315 minus 45, or 315 minus 30. 315 minus 30 would produce this sine of 285. So you could say sine of 315 minus the sine of 30 degrees. You could do it that way. Sine of 315 minus 30. And why am I using 315 and 30? Because we know the sine of 315 is a negative root 2 over 2, and the sine of 30 is a 1/2. So if we want to write them like that, there we go. Okay, so so here we have a sum for our sines, and again, going back to what we just developed, sine of an alpha minus beta is a sine, cosine, cosine, sine, and you take the same value in terms of the positive or negative. So this would become sine alpha, cosine beta, and then negative sine, cosine, cosine alpha, sine beta. Sine, cosine, cosine, sine. All right. In this case, there's our alpha, and there's our beta. So we're going to have sine of 315, cosine of 30, minus the cosine of 315, and the sine of 30. Notice we're not using the negative. That's part of the 30 angle. The negative just translates to that value right there because of our odd identities. Sine of 315. Well, we already said that happens in quadrant 4. So now we're going back to our chapter 8, chapter 7 material. So 315 is in quadrant 4 with a 45-degree reference angle, and we know that's a negative root 2 over 2. A cosine of a 30, quadrant 1, is the root 3 over 2 minus, now the cosine of a 315, quadrant 4, 45 degrees, positive. And sine of a 30, quadrant 1, we have 1/2. Simplifying this, we get negative root 6 over 2 minus root 2 over 2. And we can write that as a single fraction if we have the same denominators. We get root 6 minus root 2 over 2. And there's our answer for what the sine of 285 can be. Now, you're going to find that oftentimes you can come up with the same angle by maybe doing addition. For example, maybe instead of thinking of 285 coming from 315 minus 30, maybe you think of 285 as being 225 plus a 60. And now you're just setting this up as a sum of sines, sum of angles, instead of a difference of angles. So you still get the same answer. Just depends on which way you go, sum or difference. All right, let's try the 285. This time we'll try it with this 225 plus 60 relationship. So now we're going to set this thing up as equal to the cosine of 225 degrees plus 60. So this is our sum of cosines, double angle stuff. And with our cosine relationship, we get the saying of cosine, cosine, sine, sine. But remember, cosines are negative, meaning they're opposite of what we see here. So we have cosine of, again, there's our alpha, cosine of our beta, and then now we have to do a minus, because that's a plus, sine, alpha, sine, beta. Cosine, cosine, sine, sine. Okay, 225 for cosine. That's 45 degrees in quadrant 3, where cosines are negative. So that's a negative root 2 over 2. Cosine of a 60 is 1 over 2 in quadrant 1. Sine of a 225, also in quadrant 2 or 3. Negative root 2 over 2. And sine of a 60 is a root 3 over 2. So we do have some negative things going on right there. So that's going to be turning that into a plus. All right, so we get negative root 2 over 4. I just realized that I didn't multiply my denominators here. That's 4, that's 4, that's 4. Sorry about that. And plus root 6 over 4. Put them together, and we get a root 6 minus a root 2 over 4, or a negative root 2 plus a root 6 over 4. And there we go. I also left out my negative here. Sorry about that too. Negative root 6 minus root 2 over 4 on the top one for sine, and cosine is positive. Now, the reason I was kind of catching myself here is because in a 285 degree angle, we should be in quadrant 4, and that would mean the value of sines are going to be negative, so that is a negative value. Negative root 6 minus a root 2 over 4 is a negative value. And then here, 285 for cosines are supposed to be positive, so that's what we get here, square root of 6 minus root 2 over 4. And again, these are exact solutions. They're not simplified to, or they're not reduced to a decimal, which would probably be non-terminating or rational. So we want exact solutions. We will leave them like this, and if any rationalization has to happen, we would take care of that. But there we go. Using our sum and difference formulas for sines and cosines. Let's keep moving on. What about going the other way? where we recognize the expression here and have to figure out, did this come from the sum or difference of a sine or cosine? And again, it has to come down to, for cosine to remember, the saying is cosine, cosine, sine, sine. And for sine relationships, it's sine, cosine, cosine, sine. And remembering that cosines, we think opposite of the value that we see in between. So a plus in a situation where we're dealing with cosine, cosine, sine, sine means a negative in terms of my angles. I'm adding or subtracting. All right, so here we have a sine, cosine, cosine, sine. We know that is a relationship with angles from a sine relationship. And for right now, we'll just leave it like that and figure out, based on what we have, if I have a plus, what is that doing here? Well, for sines, what you see is what you get. So we have a situation where we're trying to equate this sine of 1 cosine 2 plus cosine 1 sine 2 into a situation where we can just simply write it as sine of sum of these two angles. And it's really as simple as this. What's my alpha? Well, there's my alpha. There's my beta. So sine of 1 degree plus 2 degrees, sine 3. There's my solution to this. And again, it just comes from the fact that sine of alpha plus beta is this. Sine of alpha, cosine of beta, cosine of alpha, sine of beta. Sine, cosine, cosine, sine. And that's the setup we have. Now let's try this over here with B. Another sine, cosine, cosine, sine, this time with a negative. So we automatically know that that's going to equate to an alpha minus a beta. And a sine, cosine, cosine, sine is a relationship of sine. So we fill it all in. Again, identifying alpha, identifying beta. We have now a 20 minus a 15, or a sine of 5 degrees. Cosines. Cosine, cosine, sine, sine. All right. We have a relationship where I'm going to be using cosines, and I got to think opposite now. And now this is going to be an alpha plus, because it's cosine, cosine, sine, sine, we're dealing with this relationship. So there again is my alpha, and there is my beta. So we have the cosine of pi over 4 plus another pi over 4, making cosine of 2 pi over 4, which is the cosine of pi over 2. So there's my relationship there. Over here, all right, I have a plus, I have a cosine, cosine, sine, sine. That means I'm going to have alpha minus now. And filling this one in, alpha beta is 75 minus 25, or cosine of 50 degrees. What about proving? Back when we were doing this from chapter 8, we said sometimes you work on both sides of the equation, but what you don't want to do is you don't want to start moving terms from the left to the right-hand side. That's a solving motion there. We're proving, which means I want to make this left-hand side look like cosecant of x. So we're going to go ahead and just work the left-hand side here. And first of all, we have a secant of some angle minus another angle. Well, remember that a secant is the same thing as a 1 over cosine of this angle theta over 2 minus x. So really, I'm just dealing with my sum cosine situation right here. And again, I got to do a little identification. There's my alpha, there's my beta, and we know that this thing is going to translate into a plus when I'm working with my sum formula, or my difference formula in this case. All right, so let's keep working at it. 1 over. This is a cosine, so we have cosine, cosine, plus sine, sine. Cosine, cosine, sine, sine. Different value of the sign, S-I-G-N, from a negative to a positive. A few things we observed here. Cosine of pi over 2. Cosine of pi over 2 is 0. So this thing just goes away to 0. Which means this whole left side is just 0. Sine of pi over 2 is 1, which means this whole right side just becomes sine of x. So now we have 1 over the sine of x, which guess what? Is equal to a cosecant x. So we have checked it out, it's proven, left side is equal to right side. We are good. This next example, going back to thinking about the angle that I have, the relationship, and which quadrant I am. So we have for our alpha, we're going to be at the interval of pi over 2 to 0. And for our beta, we're going to be in the interval of pi to pi over 2. So thinking about where those angles are, quadrant 1 angles and quadrant 2 angles. Let's do a little sketch here, because what we want to see, if we're trying to find the cosine of alpha and beta, is we need to take these sine information, these sine values here, and relate them into cosine values. So we'll do that over here. So the alpha angle, real quick sketch, right over here, there's my triangle, there's my angle alpha with an opposite side of 4 and a hypotenuse of 5. And by our Pythagorean identity or Pythagorean theorem, we know that this length here for the x is going to have to be 3. 5 squared minus 4 squared equals 3 squared. Let's do the same thing for our betas. But now, because of our identity or our interval here, we're going to be over there in that quadrant, where there's our angle beta that produces the triangle. And we have a relationship of an opposite over hypotenuse. And again, 13 squared minus 25 minus 5 squared. So 169 minus 25 is 144. We square root that, and we get a 12 at that x value there. But it's on the left-hand side, so it's going to be negative. So now we can say, why were we doing this? We're doing this to get cosine beta and cosine alphas. Cosine beta is negative 12 over 13. And cosine alpha is equal to 3 over 5. Now we can use that information to help us find cosine of alpha plus beta. So cosine, cosine, sine, sine. We're going to get cosine alpha, cosine beta. Remember that the plus there, cosine's bad. Change it. Sine alpha, sine beta. And we have those values. We have all of these values, actually. We can fill it all in. Cosine alpha, we said, was 3/5. Cosine of beta was negative 12/13 minus sine of alpha, which is 4/5, and the sine of beta, which is 5/13. Doing some simplifying here. sure I don't miss it this time. We have negative 36 over 65. And minus 20 over 65. And this finally reduces to negative 56 over 65 is what this cosine of alpha plus beta is going to equal. So there's my relationship. I think I can reduce anything there. Making sure I plugged everything in, right? I think I'm good here. Negative 36 minus 20, negative 56 over 65. And there is your ratio. So a little bit of going back to chapter 7, creating our triangles in the appropriate quadrants to find these relationships of our angles. And then using that information for our sum, in this case, of cosines.